This example is we want to look at the message signal. The message signal is just one cosine signal. It's a very, very simplified signal. That's equals to small a cosine 2 pi FEMT. You can see here FM, that's the frequency of the message. And we're assuming that FM is much, much smaller than the carrier signal. First of all, let's look at the modulated signal. Modulated signal definition, the message multiplied by the carrier, right? So carrier is big AC cosine 2 pi FCT, right? And this portion, it is the message. So you multiply it together. So this is our U of T. And now we want to reorganize this format, 2 cosine multiplied together, because it will be easier for us to take Fourier transform. Okay, we want to use triple identity. This is the one we used. Cosine multiplied by cosine, that equals to half. The cosine, the angle take difference, and then cosine, the angle take the addition. All of these formulas are in our formula sheet, so check out frequently. So now AC, small a is here, there's a half here, and then this cosine is cosine, right? We want to use the triple identity here, and this cosine multiply together, and as a result, we want to have 2 cosine sum, take the summation here. So the angle take the difference, that will be FC minus FMT, and then the angle take the sum. And then you sum them up, you divide it by 2. And here I have this coefficient taking out for each cosine signal here already, just for convenience. Now, next question is to find what is the spectrum of the modulated signal. With the spectrum, you take Fourier transform of this time domain signal, right? So we take the Fourier transform of this signal here, but this signal are 2 cosine signals. So each cosine signal are two specs, 2 delta function here. So cosine 2 pi, I use F naught T. What do we have? The Fourier transform is half the right, 2 bracket here. So your F naught is this portion or this portion, right? So let's look at the first one. The first one, delta F minus F naught. So this portion is your F naught. This is F minus F naught. That's minus FC plus FM. Okay. And then F plus F naught, that's F plus FC minus FM. That's this portion. This is the first term. In the second term, your F naught, this F naught is this portion now in the bracket. Then you plug it into the delta function here. So first delta function is delta F minus F naught, but your F naught is this quantity here. Delta F plus F naught. Your F naught is this quantity again, you plus it here. So thus we have 4 delta function here. So this is the expression for U of F. Next, we want to plot. And remember this, delta F minus F naught. Where the delta function is, that's F, and this is F naught. Delta function is here. What is the delta F plus F naught? That will be F here. That's minus F naught, right? And then for cosine signal, there is a half here. There's a half here, so there's a half here, so don't forget the scale there. Remember here, I only look at delta function here. Only look at a delta function here, so there's no scale here. The same thing here. I look at a delta function here. I don't have half at the front, so don't confuse. Let's look at this delta function here. This delta function sitting at fc plus fm, that's this. Right? And what is this delta function? That's sitting at minus fc minus fm. That's this one here. Let's use another color. What about this one? This one sitting at fc minus fm, because if you do a little reorganization here, that's f minus fc minus fm. This delta function sitting at fc minus fm, that will be this, right? We only have one left here. And this delta function, this is delta f plus this, okay, plus fc minus fm. So this delta function sitting at minus fc plus fm. This is minus fc plus fm, right? Now let's review the concept of lower sideband. Okay, I'm gonna erase this. So remember, the lower sideband is that the frequency component in the modulated signal, this is a modulated signal, the frequency component in the modulated signal lower than the FC. So if you look at here, this is FC here, this is FC. So what is a lower sideband? You only have these two specs here. So this is a lower sideband frequency components in U of F in the modulated signal. What is upper sideband component? Upper sideband components is the frequency component higher than FC, so higher than FC, right? So it contains this spec and this spec. Let's look at this two delta function here itself. There are two delta functions sitting at here. This is positive and this is a negative. I can have FC minus FM, right? So basically this is the quantity and this is a negative of this quantity. Then what is the cosine signal? This is a cosine signal, right? Whenever we see two specs in frequency domain, immediately we should reflect ourselves in time domain. That's a cosine signal, right? Okay, then cosine signal, what's the frequency? This frequency will be 2 pi fc minus fm. So you can see here, this frequency fc minus fm is lower than fc, right? Of course, this is a lower sideband. That will be lower sideband. Okay, let's look at this two specs here, and here. Whenever we see two specs in frequency domain, immediately we should know that in time domain, we're talking about cosine signal. So what's the frequency for the cosine signal? That's where the location of this delta function is sitting at. You can see here, this is fc plus f naught, and this is minus fc plus f naught. So I should say this minus fc plus f naught. You put it in the bracket here, fc plus fm. And this is minus fc plus fm, right? You can see here, this is the same quantity. See here, fc plus fm is fc plus fm. What's the cosine signal in this case? The cosine signal is 2 pi fc plus fm. So what's the frequency here from this time domain signal? We can see this is the frequency FC plus FM. So of course greater than FC. And here that is in the upper sideband. I just demonstrated how I can obtain the Fourier transform of the modulated signal using trickle identity. We can also use the modulation property directly. So modulation property is also listed in our formula sheet here. Xt cosine 2 pi f naught t time domain was the frequency domain. That's this. Now, if we want to use a modulation property here, so EMT, and this is C of t. And C of t here, we have the magnitude AC here, so don't forget that. Then we want to find out what is MF. So what's the Fourier transform of the message? And we can see here, this Fourier transform, it only contains two specs. One is at FM and minus FM. The magnitude is half A. So this is a half A and FM and minus FM. So this is our FM. So FM means you multiply by another cosine. Then forget about this AC for now. You're going to be on a scale. MF move to FC and MF move to minus FC. You take half. MF move to FC. That's here. These two specs move here. What's the scale? Scale, that's half A here. There is a big AC here. Big AC. And remember, there's a half for the modulation property. So there's quarter here. So this portion, this whole portion here, move to minus FC. What's this frequency here? You can see here, this is 0 becomes minus FC, and this portion, this point here becomes minus FC plus FM, because, and this point becomes minus FC minus FM, right? So the same thing here. This whole spectrum move to FC. So 0 become FC, and this point, this specs at FM, it becomes FC plus FM. So this is a spectrum of the modulated signal. Here we demonstrate two ways to obtain the Fourier transform. One is you use the trickle identity. The other one is use the modulation property. Either way is fine for this case. And remember, if your message signal is not cosine, if your message is other waveforms, then you need to use modulation property, because you do not have cosine multiplied by cosine together, as in this case. Now let's find out the power. So the power in the modulated signal, sometimes we say the power for U of F, and sometimes we say the power for U of T, and both statements are valid. They are both okay, because U of F and U of T, they're referring to the same signal. And power is based on a signal. Any signals has a power. And no matter what you call the signal, the time domain or frequency domain, you're referring to the same signal. So therefore, power for U of F, that's okay. That's a valid statement. And power for U of T, that's valid statement as well. Okay, so don't get confused of these two terminologies. Now, what's the power in the modulated signal? That's half AC squared multiplied by PM. What's the PM? That's the power contained in the message signal. And what is the power there? It's a cosine signal. It's a power that's a magnitude squared divided by 2. So small a squared divided by 2. Then what is the modulated power? AC squared and small a squared, right? And divided by 4, because there is a half here, there's half here, you got 4. Now, what's the power in the upper sideband and what's the power in the lower sideband? And this is easy to figure it out because the lower sideband and upper sideband, they're symmetric, right? They're symmetric. So the power for the upper sideband will be half of the total modulated power, and power in the lower sideband is half of the power in the modulated signal.